Okay, thank you very much. Yeah, today I'm going to give some overview of my research. In particular, I'm going to talk about research efficient distributed learning in large-scale systems. And for this talk, I'm first going to, since it's should be quite broad audience, I'll start by just telling a little bit about myself and general motivation for kind of the type of work I do, and then I will tell high level about some of the projects we're doing, and in the end I will maybe go a little bit deeper into one particular topic, if there is good time. Okay. So just to tell a little bit about myself, so I am actually, like Shugang said, I'm from Iceland, where I studied mathematics, so most of my background is mathematics. And then I moved to Sweden for my master's degree, where I studied actually here, KTH, in the mathematics department. And then I did my PhD at electrical engineering, moved to more like applied mathematics. And then I did like a postdoc at Harvard University, and then I came back first as a postdoc, and then I became a member, faculty member at Stockholm University in the computer science department. So where we're doing a lot of data science and machine learning and AI and distributed algorithms. Okay, so just a few words about our department. So Stockholm University, we also have huge computer science department in Stockholm University. So it's actually one of the big, I believe it's correct that we are the biggest department of any kind in Sweden with 6,000 students, in terms of students at least. And we have a lot of different types of programs, bachelor programs, master's programs, with joint programs with on health informatics together with Karolinska, and we're also starting other European projects for data science and health informatics and related topics. And we are very strong, even though I say myself, I think we're quite strong in both AI and data science. And this is kind of the area where I'm working. Okay, this is a little bit about myself, and let me then just give a small overview of what I'm going to talk about today. So first I'm going to try to give some motivations about the research I'm interested in, why I'm interested in it, and also why I think it's important. And then I will give let's say, a high-level overview of some of the topics we're working on. And then I will go a little bit deeper into one particular topic. So I try to make it still like everything at a high level. So since we have quite broad audience. Okay. So in the last few decades, we've seen major technical revolutions going from computers to internet to wireless networks, where now we're seeing a lot of everything being more and more connected with more and more devices used through our society to sense information and to try to both measure what's going on in our society, in our systems, and also try to do some intelligent decision making. So there are some studies you can see, for example, from Ericsson, that you have the number of devices, connected devices that are collecting data to try to improve all the processes in our society is estimated to be 28 billion. Okay, this is actually a bit old number. Was estimated to be 28 billion in 2021, and this is creating a multi-trillion dollar economy. Okay, so when we have all these devices, various types of nodes, then to be able to make any type of scalable decisions, whether it is for transportation networks, power systems, robotics, or any types of sensor networks, then if you want to make a scalable decision, and even if you want to make it in a real time, then we have to go from some kind of centralized operations of these systems and try to move more towards like distributed operations, where nodes become part of the decision making, get some kind of autonomy, collect their own data, and take part in the decision making, global decision making for these types of systems and networks. Okay. And at the same time, we are seeing kind of this emergence of big data. We're collecting more and more data to try to learn models. And we have similar challenges here. As a general for networks is that if we want to process all these huge data sets, then we have to be able to solve them. We need to split the data into multiple nodes and try to parallelize. So we run into similar types of challenges in most kind of a modern machine learning algorithms. And this is both of these. I mean, it's kind of, if you want to solve both in machine learning and in general decision making, the challenge is that complexity is shifting from traditional computation and shifting towards the coordination and communication of all these nodes that are collectively trying to solve huge problems. Okay, and then we of course vision when we have all these devices and networks that we are not only going to, when we collect, also they will also be collecting data, so in the end we will also be solving large-scale machine learning problems in these kind of huge networks. Okay, so this is kind of some general motivation of my work, but let me take few, let's say, like some concrete examples. Let me go through 3 concrete examples which are related to some of the projects that we are currently working on. So we're currently doing some work where we're doing this kind of a large-scale distributed decision-making, mostly driven by AI and machine learning, in water distribution and power distribution, and also when we're working with Scania on smart maintenance of trucks. So the first project that I want to tell about is actually supported here by Digital Futures, and I will provide some more details on that in a little bit, but just to motivate, the particular topic that I've been working on in this area is that it might be surprising, but in our cities, there are actually a lot of studies that show that a lot of drinking water is lost because of just leakage in the pipes. Largely because there's not a lot of investment in trying to maintain these systems that are supposed to distribute water, because water is cheap. But at the same time, we are seeing a lot of water shortages all over the world. So it's very wasteful, and repairs are expensive. So here we've been looking into how we can try to use the digitalization of our infrastructures, smart sensors throughout the systems to try to solve problems, for example, by identify leakages in these kind of systems. So what we've been working on here, just to give a very high-level overview, is that if we have a water distribution systems, how we can, let's say we have a system and there is some leakage in the system, some broken pipes, how we can use smart sensors and various types of wireless sensors to try to track what's going on inside the systems, ideally in real time, or at least in a way that allows us to do some kind of for example, predictive maintenance, or trying to identify leakage and other things like a pollution in these kind of systems, so we can then act in a intelligent way based on the actual need, because it's very expensive if you have a leak to try to identify. Because if you want to fix it, you have to know exactly where that is, because you have to dig into the ground to try to solve it. Okay, so we have some studies on it where we actually been working on how we can take these kind of sensor measurements and combine them with some kind of knowledge about the physics, because here we have a pressure systems of the pipes, how we can try to localize leakages in these systems. So this is the one topic that we've been working on, and then we've been have some ambitions in kind of combining this with intelligence maintenance and some more smart digitalization technologies.
Sindri, there, were you able to get some real data? I mean, this looks like simulated data.
Yeah. So what we had here is simulated data, and then we are in some discussion to try to get like a real data.
Okay.
And this is a project that is sponsored by Digital Futures, and where we have multiple partners, including Stockholm University and Rice. And here, this is just like one component, the component that I've been working on. But in general, here we're trying to use learning-based methods, where we're trying to have a distributed learning mechanisms to both solve or study how we can use this digitalization of the smart infrastructure, for example, water distribution networks, and make some kind of intelligence, AI-driven decision-making in the systems, where one test case is water distribution systems, and where we're working both with leakage and detecting pollutions, for example, in the systems. So we're combining it with both physical modeling, so knowledge of the systems, and also with the network design. So combining, co-designing the networking, because these nodes have to communicate, and with the actual decision making. So kind of co-design the AI and the networking tools that you need to facilitate these kind of distributed decision making. And then we have been doing this by using this very nice simulation model that is created by the EPA. It's the Energy Environmental Agency in the US. So they make it to kind of simulate the water distribution systems. And then I've been using this. So this is one project that we've been doing. So then another project that we've been working on is this also, like I say in all of my work, we have some kind of a distributed system, and we are trying to do some kind of a machine learning, distributed machine learning in some kind of a cyber-physical systems. And another case that we have been looking into is this energy transition. So where we are trying to make more, when we're trying to include more and more renewables into the energy systems, then it creates a lot of challenges because we have to use these resources kind of as they come. And then it creates also, because we have to kind of use the energy as it comes into the system. And it creates also a lot of, if there comes certainly a lot of solar or wind into the system, we have to somehow, on the demand side, we have to be able to kind of regulate that, because we don't. So this is kind of a key challenge that we see now in the energy systems. And for example, if we have a voltage on various devices, all the devices in the systems, then we have to always make sure that we maintain the voltage into some kind of secure range. And then if there comes certainly some point where there comes a lot of renewables into the system, it will it will create a lot of shock to the kind of the voltage supply in the systems that we have to address. So, and since we have here multiple nodes throughout the systems that have local voltage, and they can typically do something about it by injecting what's called reactive power. So then we've been looking into how we can create distributed AI-based decision making for trying to regularize, make a local decisions on the nodes to kind of solve the global problem that we are looking into. So here we have been looking both at advanced simulation-based models, and then we are taking these kind of the decision-making tools that we learn from the simulation, and then we are testing them on real hardware. Okay, and this is also a project that was initially with Digital Futures, and also with Professor Katie Yates, and also in Berkeley. But then now we have recently got also more funding to continue this with Hitachi Energy, and also by Vinova. So this is funded by Vinova. So just to take some simple examples. So the goal here is that if we kind of want to, if we have multiple nodes, we want them to learn to make decisions to stabilize the voltage throughout the system. So we can see here, if we have a lot of voltages on some nodes, and we have not done this kind of distributed decision making, we can see that we can violate the voltages at various times. So it will create insecurities in the system. Whereas if we use, for example, here our approach is we manage to kind of maintain the voltages within a feasible range. without the nodes having to communicate, just based on local measurements. Okay. So then the third, let's say, high-level presentation of some of the projects where I've been involved is also another Vinnova-supported project, which is together with a colleague, Tony, and also with Scania. And also there's a professor in KTH and also in Linköping. So, and here we're also working on similar topics where we have multiple nodes. In this case, we have a lot of trucks, Scania trucks. And Scania, they want to try to, let's say, own the full supply chain. They don't only want to sell trucks, they also want to service the trucks. So, and to service the trucks, they also have to maintain the truck. And then what they want to do is that they want to use all these sensors on the trucks to try to call in the trucks at the optimal timing to the workshop to service them at the optimal time. Because, for example, if they don't want to service them too early, because exactly. And then also, certainly, they don't want to service them so late that they break down. And if they have sensitive cargo, like, I don't know, like some frozen stuff, it will get ruined. So then we have some kind of a cost optimization problem based on all these kind of sensor measurements on the data, where we somehow want to balance calling them in too early and calling them in too late. So this is a very interesting project where we also have this kind of a distributed AI-based decision-making in kind of real systems.
Have you tested some of these?
Yeah, we've tested. So we are working actually very closely with Scania, and so there are a lot of engineers from there. And then we have access to real data, and the plan is I mean, they are interested in putting this into production. So.
And just out of curiosity, I know it's not really the core of your project, but which are the most influential factors for the truck failure?
Okay. So we're actually doing this for multiple parts of the machine and engine. So then it's a little bit. So we have been looking at different components, but I don't have good insights into which component is like the first. But I would say, I mean, so some of them are, let's say, I don't know, less sensitive, and some of them are more sensitive. I guess the battery is something where you have when you can take a lot of measurements and you have good models, so you can try to do good optimizations there. Then there's other components which have more and some kind of uncertainty about them.
When you look at the size here, so are we talking about 100,000 components, 20 different models, or millions, or 10 or 100? Can you say a little bit on the data?
Yeah, so the data is, so we have for different components. So then we have from different trucks, the similar components. So it could be, for example, a battery. And then what we have been doing is that we both have been looking at data from batteries and trying to create simulation models. Mm-hmm. And then based on the simulation models, try to optimize. And then we also have just some data on different components. And then
I see. So it's not just, so to say, failure models. You also have dynamical models of component.
Yeah, there's also a little bit of, because the guys in Linköping are doing more like the physical models.
I see.
And then we are doing more like the predictive maintenance and like trying to optimize the cost. So, because there's also, I mean, different failures have different costs, and also certainly, it's like it's cheaper to take the car a little bit too early rather than a little bit too late. So then this types of kind of sensitivity analysis.
Yeah, I guess it's also going to change a lot once the electrical vehicles become like the mainstream.
Yeah.
Because I don't know much, but I would guess an electrical motor has less parts that can fail compared to a internal combustion engine.
I can imagine, but I don't have good insights on it.
Okay. No, just correct. Cool.
Okay, so this is a little bit of overview of some of the projects we're doing, and I'm happy to discuss this more. And you can message me, or we can continue discussing after this. And discuss this more. So this is a little bit like in general, and let me now maybe go a little bit more technical and tell a little bit about particular problem that we've been working on and gone very deeply into. And I must say, kind of the main contributor actually of this is Chuyang, who's here. So, so it is asynchronous machine learning. So, and this is a joint work with Chuyang, who's here, who's been leading this. Has gone very deeply into this problem. And then we've also been working with Hamid, who's an ABB now, and Mikael, who is a professor in KTH. So we have a couple of papers, but I guess I will just have time to present the first one, is to go a little bit in detail. But we had both last year in ICML and also this year in ICML some nice work on this. And then also we have at previous CDC, we had also some nice results on this problem, which is asynchronous machine learning. So let me now just go a little bit into asynchronous learning, tell you a little bit kind of the main ideas, why these problems are important and interesting, and then I will go a little bit into the contributions. Okay. So in all these kind of distributed machine learning type of setups, we typically have multiple nodes. We often have multiple workers, and then a typical setup, one setup at least. I mean, I believe that many of the ideas in principle should work in various types of distributed setups, but we have kind of nailed them quite well down here when we have this kind of a master worker setup. So the idea here is that we have a master that is maybe orchestrating an algorithm, and then we have multiple workers that do some kind of a smaller task. So we kind of distribute the tasks between these workers. It could be either that the workers might have local data, so it could be all the workers have some local data they're not sharing with the master. So this is, for example, the case I illustrate here. So for example, if you look at this optimization problem, then we are trying to minimize some variable X. It could be like a model, could be a neural network model or logistic regression model or similar, where we want to find the average over the data of or the objective functions of all the n nodes, all the n worker nodes. Okay. So if you have a problem like this and you want to solve it in this type of distributed manner, then I mean one very simple solution is that you can do a gradient descent. You can say to all the workers, compute. Here's a model. Compute local gradient based on this model and send me back the gradient. Okay, and so this is what we do here. And this is a good algorithm, works well, and the theory is solid. I mean, it's been studied very thoroughly. Okay. So, and this is what we call a synchronous algorithm, because here the master is essentially sending to all the nodes a variable, and then all the nodes are sending back a gradient. And the master here needs to wait for all the nodes to send the gradients before it can do anything. So this is very nice because the theory is solid and it should work. But what is can be a little bit a drawback of this is that the master node has to wait for all the nodes to do anything. So it means essentially that if there's one node that is very slow all the time, then the master always has to wait for that node before it can do anything. So this has motivated asynchronous methods, which are quite popular in these kind of distributed optimization and machine learning setups, where the master node is not waiting. The master node is just processing all the time the information as it comes. Okay, so we can model this as follows. So here we have a master. The master will send, for example, to one of the nodes or to the nodes a model, and then some node sends back its gradient. So relate to it that node's private data, and then the master node will just directly do some kind of gradient descent based on the best knowledge of all the gradients it has at this time. Okay, so this is better and typically works, but is faster in practice because here the master node is just processing all the information as it comes. It doesn't have to wait. But the challenge here is that it's more difficult to analyze. So we have been looking in detail into kind of how to both study these types of algorithms and how we can improve them. So I come to that in a little bit. Okay, so these types of asynchronous methods have been studied quite thoroughly, or reasonably thoroughly, and they have been shown to work very nicely in practice. But when you look at the theoretical results, then there is one huge drawback, which is that almost all of the theoretical works in this domain, they will assume that we have a worst case, that we have some kind of a worst case delay. We have some kind of a, let's say, worst case delay on how old the information is from all the nodes. And then we will use this worst case delay to tune the parameters, the hyperparameters of the algorithm, so the step size. So this is very bad because of two reasons. So first of all, in practice, we almost never know a worst case delay. We cannot know in a system what's the worst case that can happen. Secondly, even if we would know a worst case, it would be very bad to use it to tune an algorithm, because it will make the corresponding step sizes very small and conservative. Because typically we are tuning them as 1 over the worst case step size. So this is very bad. So our solution to this, or our idea that we proposed in this paper, is to study, instead of using a worst case delay, making an assumption on the worst case delay, we just take the actual delay. So if you send me information, I'm not using a hypothetical worst case delay, I'm just looking at the actual delay. And then I'm using the actual delay in the step size, tune the step size, and then I will get much larger step sizes and still will be able to guarantee convergence of the algorithm. So this is the kind of our main idea here. Okay. And just to motivate, so to kind of really illustrate that in real systems, we often have we are typically not always getting a worst case delay. We're trying to get some kind of understanding of the kind of delay distributions in the systems. So we have actually here plotted. We have actually here done some experiments where we had a 10-core machine. We solved, I believe, logistic regression in a 10-core machine. And then we just looked at the statistics of the actual delay distributions that we observed when we were solving this problem on a 10-core machine. Here we're looking at in these three figures, we're looking at a histogram that tells us the delay distribution, when the delay is like how old the information is in terms of number of iterations. And then we can see the delay distribution here. So it's for 3 different data sets. So it's a RCV1, MNIST, and CFAR. So it's a classic baseline data sets used in machine learning. Okay. Then we can see really that we always have this kind of a almost normal distribution of delays. And we can see that, I mean, if you would use the worst case delay, the worst case delay is, I mean, both probably it's going to be, we usually don't know it. And anyway, it's going to be quite far away from kind of the average delay, or the real delays that we are most often seeing. Okay. So, and then what we have done here in the first paper that I will present, I don't think I will have time to present all the works, but I have to discuss them if there's any after the talks, or you can send me an email if there's any questions. Okay, so here we look at this problem, and just to make everything concrete, kind of tell exactly about the assumptions we make and so on. The model we consider is that the model we consider, where this is the basic kind of idea that we're going to follow, is that we're going to consider, we're going to minimize some loss function. Here, loss function is f, and the loss function should be smooth, but it doesn't have to be. It can be non-convex. It's fine if so it can be like a neural network training or something similar, plus a regularization if we want to, which can be non-smooth, but should be comics. So for example, if you want to have a projection, so if you have constraints, or if you have to have some kind of a L1 regularization or L2 regularization, depending on what kind of regularization you want for your learning program. Then in this paper, I mean, we consider two different setups. So we both consider this setup that I mentioned in the beginning, where I have an objective function, where we take an average of where we have the data is distributed between multiple nodes, and we try to optimize the average between the data of all the different nodes, and then we can do something like a distributed gradient descent, or proximal version of that, since we have the regularization function here, and then we can do the asynchronous version of this asynchronous gradient descent. So we're doing where the master node is not waiting for all the most recent information from all the nodes, it's just kind of continuously processing the information it currently has. And then we also consider this kind of block coordinate descent setup, where the master node is, or where the nodes are randomly choosing a block. If for example, if the decision vector is very high dimensional, and then the nodes are just randomly choosing some part of the decision vector and then processing it and kind of working on different blocks at a different time or at the same time. Okay, so these are both of the algorithms that we consider, but let me just focus more on the first one, since. But I'm happy to discuss the other one also after the talk. So we don't. Okay, so the assumptions we make in both of the cases is that we make the assumptions that we have a Lipschitz continuous gradient, so we have a L-smooth problem. And then we define this. So then what we are going to do is that kind of our main goal is to try to adaptively tune the step size based on the actual delays instead of the real delays. And then our kind of first contribution is to show that if we have, if we define here, let's say we have multiple nodes, and we define tau k as from all the nodes where we have received currently information, we let tau k be kind of the largest delay we have currently received from all the nodes. Then we show that if we have this, we call it step size principle. If the step size is bounded by something that is proportional to 1 over Lipschitz constant, which is the typical step size for the synchronous algorithm, minus this kind of step size integrals over the last few delays, then we can ensure that we, for non-convex problems and also convex problems, that we converge as proportional to 1 over the step size integral. Okay, and this is this type of results is something similar you would observe for also if you for most types of algorithms, is that you get the convergence rate is something like 1 over the step size integral. But the reason we are getting, and I will show in a little bit why we will get much better theoretical convergence, is that we can allow, in our case, the step size can be much bigger than, or can be bigger than if we use, for example, the worst case delay to tune the step size. So I'll show this a little bit. And then we also get, if we have strongly convex problems, we will converge at a linear rate proportional to the step size integral. So often people, for example, for synchronous algorithms, this step size integral will be something like 1 over t if the step size is constant. But here it's going to be just the step size integral, and we can, with our conditions, we can make the step sizes larger and get faster convergence. Okay. So the step size integral is what we have here. So it's essentially that we make the step size, so we tune the step size. Oops. So it's something like we need this condition here to hold, and just to kind of illustrate kind of how we can do this, because this is quite a general condition. So we will just show how we can make this kind of realize this easily for two different let's say, work this out to make it easy to implement 2 different cases. So we introduced this adaptive 1 and adaptive 2. So adaptive 2 is something where we essentially allow the step size. We have like a step size budget that we cannot. So because this lambda prime here, it's something like if you had asynchronous algorithms, the largest step size that we can choose while still have a stable algorithm. So here, essentially, we just have some kind of a budget. This is our budget, and then over the last tau k, so that based on how many delay, like how old the information is we have, so we sum over how old the information that we actually have is, and then that's like our step size budget. And then if we make sure that we don't go over this budget, then we can ensure that the algorithm will be stable and will converge. The other adaptive step size is something quite, let's say, I would say intuitive, because typically when people are tuning these kind of algorithms and make assumptions on the worst case delay, the step size they choose is something like a gamma prime. So gamma here would be like 1 over L, so 1 over Lipschitz constant. So here it would be 1 over L times tau max, where tau max is the worst case delay. Okay, but what we wanted to do here is to get some kind of similar step size where we use the actual delay instead of the worst case delay. But what we realized actually is that if we use that, if we just use gamma over tau k, then we will get something we can show, but just by providing problems, is that we can really show that then the algorithm will be unstable on some simple cases. So this, in general, that will not work. But if we create similar type of rule, which is almost the same, but use this step size rule, where we just make sure that we choose this step size, this ideal step size that we want to use, except if and still just make sure that we satisfy this kind of budget constraints, then we can make the same step size work. So if we would not have this budget constraints, then we can create very simple counterexamples showing that the algorithm will not be stable. Okay, so this is really necessary, or so this step size rule here, or step size principle. Okay. Then, since we are short of time, let me just go through kind of these quickly, so I can go to the kind of some illustrations. So here we just show that we really we compare this to the kind of the worst, to the best known results currently, and we just essentially show that if you use the worst case delay assumptions, then we can ensure that we get faster convergence. Okay, but I think maybe a more intuitive way to kind of illustrate kind of why we really are improving the convergence of these algorithms is that if you look at kind of a real or some hypothetical delay distributions. So here in the top plot we are looking at delay distributions. So here we have a delay over time. So in the first line, so we have the delay could be between 0 and tau, where tau is, let's say, our worst case delay. So here in the first column, we always have a worst case delay. In the second column, we have some kind of random delay. In the third column, we just have something like we usually don't have a delay, and then at one point we get a big delay. So if you would, so then we can look here at the step sizes we can choose, and we can see, for example, here if we have essentially the message here is that if we have a worst case delay in our system always, if delay distribution is always worst case, then in the end what will happen is that of course we cannot improve it, because then we also have to choose our step size adapted to the worst case. And we can see that here in the step size integral. So the step size integral here will be similar to the step size integral if we would use the worst case delay to tune the step sizes. But on the other hand, if we have something like a more realistic delay distributions, like we have here, so then we can see that the step size integrals that we use with our step size is growing much faster than if we would use the worst case delay. So you can see here, and the convergence rate is directly inversely proportional to the this stepsize integral. So you can see the stepsize integral is growing much faster if the delay are not always worst case, if they are something between. And even if you have something that is just worst case, let's say one time, like a burst delay, then it's very bad to tune the stepsize based on the worst case delay. But if you use our stepsize rules, then you can see that we get a much faster convergence. Okay. So let me just conclude with just showing a few experiments. So here we've done like a logistic regression with a non-smooth regularization on 3 different data sets. So we run this on with 8 workers on a 10-core machine. And then here we had this distributed asynchronous gradient descent. So here you can see the 2 adaptive stepsizes compared to the current state-of-the-art algorithm that still has, let's say, a provable convergence. So it's provable. So it's not like we've done hyperparameter tuning to tune the parameters, but we're tuning the parameters based on what the theoretically guaranteed to converge. So then we can see that, and we are also choosing our algorithms based on what is theoretically guaranteed to converge. And you can see that there's a big improvement from if you use the current best known stepsize selection compared to our stepsize selection. So we are converging, I don't know, like at least 2 times faster than competitor here in all of these cases. I mean, that is this, and this is if we do the asynchronous gradient descent, and then we also did asynchronous block coordinate descent, and we got even more impressive results. So you can see, I mean, if you compare to the best known stepsize selections again that are guaranteed to be stable and converge, then we get and we are getting huge improvement on all of these data sets. Okay. So we have some other results, but maybe I can just wrap up since we're out of time. So in this talk, I first talked a little bit about kind of my general research and also about some of the projects that we have in water distribution systems, power systems, and also in smart maintenance for trucks. And then I presented this work where we are trying to do, where we're doing this asynchronous distributed machine learning, where in general, I maybe one key takeaway is that in general, I think there has been a lot of focus in a lot of theory on worst case analysis, on the worst case assumptions, for example, on the systems or on the algorithms. But we are trying to take a step a little bit away from that and trying to do more like adapt to the real things that happens in the systems. For example, in this case, if you tune your parameters based on the worst case, and the worst case almost never happens, but what is actually happening is something much more relaxed than the worst case. That if you're tuning your algorithm to the worst case, it's going to be you're not getting the full efficiency of these algorithms. So, and I think in general, just that adaptivity or adaptive to the actual data that you see is usually much more beneficial than tuning it to the worst case. And I think one of the challenges here is trying to, of course, you can do it we have some heuristics to do it, but then trying to bridge these 2 things, the theoretical results that guarantee convergence and also are adaptive to not the worst case, but to the actual case, is something I think can provide a lot of improvements in for these kind of algorithms and systems. Okay, thank you. So I have to take this in.
Very good. I have a couple of questions, very, very interesting. I actually never thought it was going to be so important to when you show there the graphs, like the difference is huge between, adapting and not adapting. And I have a couple of questions, and, is the step size or the learning rate like the only variable that really affects the learning process when there's these delays, or are there other variables? I know it depends on the algorithm, right?
Yeah.
But in your experience, are there any other variables that also affect the?
Yeah, as you know that what we're doing here is that we are not doing stochastic gradient, but we're doing like a deterministic or like a full batch gradient. So, but then if you do stochastic gradients, then certainly there's more parameters because then you have like a batch size and you have other things to tune. But when you do here a gradient, I would say that the step size here is when you just do a gradient, like if you don't have a momentum or anything similar, I mean, then the step size is really the kind of the main parameter to tune.
Yeah, because it will be interesting, with the mini batch grading descent, you can either choose, okay, based on your delay, I'm gonna increase or decrease your batch size. You could, increase thinking that you have more time to process and then send back, or decrease because you're too slow, so we're not gonna give you as much data.
Yeah, so I think there's a lot of things that we can try to kind of adapt and adjust. I mean, once you start to think about these kind of more algorithms where you have more tuning to do, but then of course at the same time, when you have more space, it become more to be more complicated to study.
Of course. And going back to one of the figures that you showed, I think just as a suggestion, yes, it would be also very interesting to see how it would compare to a scenario where there's no delay and you just have the same, let's say, step size for everything.
Yeah. So one nice thing is, like, for example, if you use our types of step size, if there turns out to be no delay, we are just going to do a gradient descent.
Yes.
Like, not typical like a step size that you would use for gradient descent.
Yeah.
Like a synchronous one. Whereas if you're tuning the steps, like the parameters based on the worst case, then you're not taking advantage of that.
Yeah.
Even if there turns out to be no delay in the actual realization that you look at. So.
Yeah. So yes, cool. Because if everything is working perfectly, then your proposed method also adapts to that.
Yeah, exactly.
Okay.
Whereas if you are tuning everything based on the worst case, then you are just always.
Yeah, it's a bit. I remember when I was doing my undergrad, we would talk about quick sort and merge sort.
Yeah.
And like quick sort had a better worst case, but merge sort had a better average case.
Yeah.
So in practice, everyone was just using merge sort. Even if it had like a lower, I don't know how to say it, but the O of like lower worst case.
Yeah, exactly.
Yeah. Cool. And I don't know if more questions.
Or some question maybe. So there's something in the chat maybe.
Yeah, there are a couple of questions in the chat, but it was about the talk.
Okay.
Okay. Good.
Happy to if you want to email me or discuss this more. I'm happy to take more discussion. Or Shuang is here also. It could also message to Shuang.
Thank you very much.